Second.
Alright, first of all, let's look at this question with the CD under the topic rotation of a rigid body about a fixed axis. Alright, so we said that a CD would spin at different speeds depending on which part of the CD is being read from the laser. Right? We use this formula, which is the angular speed, that's the speed that a point is rotating at in rads per second, is equal to the tangential velocity of the point. This tangential velocity is just the velocity of something like a linear velocity. It is the velocity in the direction of a tangent that will pass through this point. Right? Remember we said the laser that's reading this CD would only hover over a particular point at a time, and according to how the laser would view the point, it would seem as though the point is going in a straight line. Right? Now, a straight line through a point that's moving in a circle is a tangent. So the velocity of this, the angular velocity of this point would be equal to the tangential velocity divided by the radius. Good. Now, in this question, they asked to find the angular speed of the disk in revolutions per minute when it's being read from the innermost first track and the outermost final track. Right? So they just want two speeds, innermost track and the outermost final track. We know the formulas. Velocity is equal to, omega is equal to velocity, linear velocity or tangential velocity divided by the radius. So, well, the question did say a typical CD, the velocity, which is the tangential velocity or the velocity of the laser, is 1.3 meters per second. So, since they're asking for the angular speed, we just use the velocity, which is 1.3 meters per second, divided by the radius for the innermost track, and we will get 57 rads per second. We could convert that to that amount of revs per minute. Next, we do it for the outer track, right? For the outer track, we would have I hope this thing is not too blurry. For the outer track, we do the same calculations, except, alright, I think it's clear now. Yeah, same calculation. It's the same tangential speed, just that the radius is different for the outer track because they're reading from the other edge of the disc. Good. B part. The maximum playing time of a standard music disc is 74 minutes and 33 seconds. How many revolutions does the disc make at during that time? Right? So how many revolutions? Well, they want us to find what we could do is find the total angular distance that's traveled, right? And we know for every angular distance of 360 degrees, it actually made one revolution. So we go to the angular equations of motion, right? And we use the short one, which I say I don't really like using. I guess, well, for the CD in this case where we start with one velocity and end up with the next velocity and one angular velocity and end up with the next angular velocity later down, we could use this formula as a very short means of getting the answer. So for this question, we know we went from 57 rads per second at the innermost track, and we went right up to, we went to 57, we had 57 rads per second, and then we went down to 22 rads per second. Remember we said the CD spins the fastest when it's reading the innermost track. Good. So we put 57 for omega I and 22 for omega F in this formula, And we put in the time. They said the time was set to 4 minutes and 33 seconds. We convert all that to seconds. We put it in this fourth equation of motion formula as this, and we get the answer. Then we convert this in rads to revolutions by so how many? We have 1.8 times 10 to the 5. But when you guys put this in your calculator, put this in your calculator, you wouldn't get the answer. Might not look like this. It will look like something bigger. We will discuss these things on Monday, right? Or I think we might discuss them on Wednesday. It depends on when you guys when you guys actually see this video and do the calculations for yourself, right? Now, in converting rads to revolutions, we know that the angle in degrees, we divide whatever angle in degrees by 360, we get the revolutions. If the angle is in rads, we divide the angle by 2 pi, and we get how much revolutions we have. So that's 2.8 times 10 to the 4 revolutions. Now finally, the angular acceleration over this period, we would use the formula that resembles V is equal to U plus AT, right? And make A, the one that resembles that will be omega, delta omega is equal to, no, V equal U plus AT, will be omega F is equal to omega I plus alpha times T. And we make alpha the subject of the formula, and we put in our initial and final velocity and divide by the time, and we get what the acceleration was, right, for this disk. I hope you guys can see. All right, good. Next thing we looked at was the torque question. I think this one was simple. This one was very simple. Net torque on a cylinder. I just have to remember torque was force times distance, and that any torque that would cause a clockwise moment will be called a negative torque, and what would cause an anti-clockwise moment we call a positive torque. Right? I think we got through really fine with this question. Right? Just please make a mental note of every question we'll do in this video, because these are the examples you would have to know for the test. For the next test on Friday, and for the final exam. Right? Good. The next topic we would have done would be oscillations. We went on to oscillations and mechanical waves. Right now, some important things to know about this. You guys remember the two types of waves, mechanical waves and electromagnetic waves, and we said that what's the difference? Mechanical waves need a medium to propagate. However, electromagnetic waves do not need any medium to propagate. With the mechanical waves, like for instance sound waves, they need the molecules of the air to actually propagate, for the wave to move. However, electromagnetic waves like television signals and such, you don't need any physical medium to facilitate their movement or propagation. Right? For the most part, we had to go through a lot of different formulas here: period, frequency, velocity of a particle in circular harmonic motion, and there was a lot of formulas that we discussed. But what is SHM? I would not reinvent the wheel by saying all those things again, but we will focus on the examples, right? Because as I said, what you will have to know for the test is mainly the examples. So please look at this video and reattempt every question you see me mention in this video. Please, and come Wednesday asking relevant questions about the questions we looked at here, right? All right, let's continue. Good. So for this question, it says a block connected on a light spring for which the force constant is 5 newtons per meter is free to oscillate on a frictionless horizontal surface. The block is displaced 5 cm from equilibrium and released from rest, as in figure 15.6. Right? We pull it, we stretch it 5 cm and then release it. So right away we know the amplitude, it will go to a height of 5 cm. But we said if it's going horizontal or vertical, it's the same calculation. It will go to 5 cm, go to 0, go to negative 5, 0, 5, 0. And that's how it would go, because we pulled it to 5 cm from an equilibrium position and then release it. Find the period of its motion. Now, this question should be very, very easy for you because it is heavily formula based. You will have these formulas available to you. Now, what we will do is just basically plug it in these formulas. This thing will be really simple. So they gave us the mass, and this A is the amplitude, and they gave us the spring constant K. They said find the period of its motion. We know, and we have a formula for a period which says T is equal to 2 pi over omega. That is right here where my fingers. 2 pi over omega is T. But we don't know omega. But we know next formula that says omega is equal to the square root of K over M. So we can use the K and the M they gave us, put it in this formula, and get omega is equal to 5 rads per second. Now once we get to omega, we can use our previous formula and find T. So our period of oscillation is 1.26 seconds. For the maximum speed of the block, we use this formula, V max is equal to omega times A, which we also discussed. And for the maximum acceleration of the block, we use A max is equal to omega squared times A. And finally, the question says express the position, velocity, and acceleration of the block as functions of time in SI units. So the SI units, they just mean that you just keep using seconds for every time and meters for all the distances. Don't put it in cm or anything, right? So we just use the formulas we know for displacement, velocity, and acceleration. And we put it, well, what we had for omega and A, we multiply these together and we get these answers. Now, if you're asked to now give the position, velocity, and acceleration at t equal 3 seconds, for instance, you use these exact formulas and just put t equal 3 in each, here, here, and here. Please remember to use your brackets and to leave your calculator in rads for this, because watch, omega is in rads per second. Right? We will ignore the pothole question for now. You wouldn't see that back again. Alright, wave motion. Oh, wave motion is when we look at electromagnetic versus mechanical waves. The two types of waves and such, and propagation. Alright, remember we said we spoke about transverse and longitudinal waves. So a traveling wave that causes elements of a disturbed medium to move perpendicular to the surface to the direction of propagation is a transverse wave. And a traveling wave or a pulse that causes the elements of the medium to move parallel to the direction of propagation is called a longitudinal wave. Right, and then we had a class where we were looking at a pulse moving, a traveling pulse. See, we have a pulse here and it's traveling to the right. That was a class. We're not going to go into detail of the derivation of all these formulas. As I said, we're using this video to focus on the examples. Now, in the example, we basically have, we will always have they will give us the formula associated with the this formula, which is the definition of this pulse. This pulse is defined by this formula. That is the definition of the pulse, right? It says, find the expression for the wave function at time equals 0, at t equals 0, t equals 1, and t is equal to 2. Now, if they ask this, all you would have to do is, you see what it says, is just find the expression for the wave function. This is already the expression for the wave function. Just at time equals 0, time equals 1 second, time equals 2 seconds, all you have to do is put these same values 0, 1, and 2 into 40 into this equation. So you'd put 2 divided by x minus 3 times 0 squared plus 1, then 2 divided by x minus 3 times 1 squared plus 1, and 2 divided by x minus 3 times 2 squared plus 1. And we have that there. And seriously, that is all we had to do. Now, going further on, we might have said that there is an element some distance along the direction of this pulse is traveling, 5 cm, 2 cm, 4 cm. Of course, we will convert all the cms to meters. Now, if we say what will be the height of an element that is 10 meters away from this pulse in a time 0 seconds, 1 second, and 2 seconds, all you do is put 10 for the expression that represents 0 seconds, and what number you get here, that's the height. For the expression that represents 1 second, you put 10 here and get the height of the object at 1 second after, and for 2 seconds after, you put 10 in this equation, right? Remember, you guys do the same math for yourself, and come on Wednesday with the whatever questions you do have. For a traveling sinusoidal wave now, it says the entire wave is traveling. Sinusoidal wave traveling in the positive x direction has an amplitude of 15 and a wavelength of 40 cm, which we will convert to meters, of course, and the frequency of 8 hertz. The vertical position of an element in the medium at time, or we wouldn't use this second part of the question in the test. We can only focus on the first part. We wouldn't worry with the element in the medium. So we'll just focus on finding the wave number, period, angular frequency, and speed of this wave, right? And those formulas are to do these things is very heavily formula based. Once again, what we would do is use these formulas for wave number and angular frequency, etc. And I will give you these formulas. You don't have to worry, right? So use these formulas and just substitute the relevant values. Now, I don't like what they did here because they used the entire 40 and put it in rads per minute. What I want you guys to do is use not 40 cm but 0.4 meters, and your answer would be in rads per second, right? Don't use anything in meters, in cm, sorry. So yeah, so just use the formula for wave number, for angular frequency, and for period. So to find the wave number, we know they gave us the wavelength, which is lambda. So we just plug it in here. We get for the wave number. Sorry, for the wave number. For the period, they give us the frequency 8. We know period is 1 over frequency, and for the angular frequency is 2 pi times the frequency, 2 pi times 8, and we get the angular frequency. And the speed also, that's one simple formula. This formula was used. V is equal to lambda times f. We substitute and we get the speed here. Right, we would not look at the second part again for the test. Now, the final thing we did was sound waves, which I will cover in the next video. Right, so this was more specific to this was a very specific topic, sound waves. No, uh, I said we will skip all the long discussions and focus on the examples. Right, let's focus on the examples. Right, you guys please do back these questions. So first example, 17.1, it says the faintest sounds a human can hear, the human ear can detect at the frequency of 1,000 hertz correspond to an intensity of about 1 times 10 to the minus 12 watts per meter squared, which is called the threshold of hearing. The loudest sounds the human ear can tolerate at this frequency correspond to an intensity of about 1 meter watts per meter squared. The threshold of pain. Determine the pressure amplitude and the displacement amplitude associated with these two limits. All right. So we want to find two things here: pressure amplitude and displacement amplitude. I think this test is more just to see if you have an understanding of how to apply these formulas, because you will get the formula for pressure amplitude and displacement amplitude on the paper, right? So it's really truly a test of using the formula. That's how it would come across in the exam. What I want you guys to do is, when you're doing these questions, I want you to make your own formula sheet. I'm not gonna give you a formula sheet Friday for the next test. I want you guys to make a formula sheet and make a note of every formula you're going to be using, and I'm going to allow you to bring in the formula sheet in the exam. Once I don't see if I see anything else except a formula there, of course I'm going to scrap your sheet, right? Good. So yeah, you will get these formulas. So it says determine the pressure amplitude, which is the maximum pressure, and the displacement amplitude, which is the maximum displacement associated with this intensity and this intensity. Well, the formula for the pressure amplitude, or the maximum pressure, is just the square root of 2 multiplied by uh, rho times V times I. Now the rho would be 1.2 kg per meter squared. Now this rho value would just be the density of air. So I will still give you the constant rho in the density of air. Alright. Now density air being 1.2 kg per meter cube. Yeah, so the Pmax formula is just 2 times rho times V times I. We know the velocity is equal to 343 meters per second, which is the velocity of, or the speed of sound waves in air. So it's just density times speed times the intensity. We plug this thing in this formula and get this answer, right? So yes, in the test I will give you what is, you don't have to remember the 343 meters per second is the speed of sound wave in air. You don't have to remember the density of air. Because I will give you those things, but please just plug us in the formula the right way. I don't want to make it too hard for you. You guys did really good in the first exam. Good. Next, to find the displacement amplitude, we use this formula, which says is P max divided by the density times velocity multiplied by the angular frequency, right? And remember, angular frequency or angular velocity is equal to 2 pi times f, right? And you said the frequency of this thing is 1,000 hertz. So 2 pi f is here, and here we have the same velocity of the sound and the pressure. Once again, no, sorry, not the pressure, the density of the air here. So we use P max divided by density times the velocity times the angular frequency, and we get this number. This will be a very, very, very small number in your calculator, right? And it says this in a very similar manner: the loudest sounds human ear can tolerate is this number and this number. So I want you guys to get these two answers. Just do the same thing again, but for the you notice these values only corresponded. They use the force intensity 1 times 10 to the minus 12, because this was for the threshold of hearing. So this and this, use the threshold of pain values and get these two answers, and then you can say you're ready. For then we went on intensity variations of a point source. A point source emits sound waves with an average power output of 80 watts. Find the intensity 3 meters from the source. Well, again, you will get the. Please make a note of this formula so you can put it in your formula sheet. You can't say you can't give the formula a label. That means that is for the intensity of a sound wave at a distance. That's what this formula is. Intensity of a sound wave. Oh, it's not focused. So this formula is the intensity of a sound wave at a distance, at some distance, right? So they asked for the intensity at a distance of 3 meters. We put now average power, put now distance equal 3 meters, and we square it and we get the intensity. It's very simple. And then it says find the distance at which the intensity of the sound is 1 times 10 to the minus 8. Well, we use this same formula. They give us the intensity and ask for the distance. We use the same formula and make R the subject of the formula, and that's what they did here and got that answer. Right. And next very important question: sound levels. That's where we spoke about decibels. Alright, so for sound levels, two identical machines are positioned at the same distance from a worker. The intensity of sound delivered by each operating machine at the worker's location is 2 times 10 to the minus 7 watts per meter squared. Find the sound level heard by the worker when one machine is operating, and then it says find the sound level heard by the worker when two machines are operating. Well, for sound level, we use this formula: beta is equal to 10 log I, which is the intensity, divided by I naught, which is a reference to density, which is the threshold of hearing, which is this number, which I will also give you. All of the constants you have to remember: the speed of sound in ear, the density of ear, this what's this? The threshold of hearing. You will get all these values in the test, right? And anything else you're worried about not remembering, just ask me after seeing this video, right? Good. So we want to the intensity of the sound level heard by the worker when one machine is operating. Well, we just use this formula: 10 log I. Give us the intensity of one of these things is 2 times 10 to the minus 7 watts per meter squared. So just put that value up here and put I naught value, which is 1 times 10 to the minus 12 watts per meter squared, down there. And that's it. So just put that and that there. You can get a number 50. Log it, then multiply by 10, you get 53 dB. For two machines, instead of putting 2, you put 2 times 2, which is 4. You do the same thing again and you get 56 decibels. Alright, now the final thing we will look at is this broken clock radio. Next very important question. You guys, I'm sure you recognize that what I give you as in class, like examples, and what I tell you to work and such, it's like very similar things come in the exam. very similar. It's like understanding these things is basically like getting your exam right away. So what I want you to do is try to do these things by yourself. And if you're not getting them out, come to class and talk. So sorry, I stick at this point, and then don't go home until you get it, right? Don't come to class and just be quiet and you don't understand, right? And don't come not even attempting the question, you guys. You really need to bounce back from the first test, right? Good. So it says your clock radio awakens you with a steady rotating sound of frequency 600 hertz. One morning it malfunctions and can't be turned off, so you throw the clock out of the window and you want to know, as you listen to the clock radio falling, what frequency do you hear just before it's striking the ground? So this question mixed projectiles with the Doppler effect. Well, we already spoke about the Doppler effect. As I said, this is a small recap. We're just going to look at formulas and the examples. So we know the frequency that you perceive would change. Like if something is going a certain moving, if a sound is oscillating, a sound wave is going to a certain frequency. If that sound wave if the thing causing the sound wave is going closer and closer towards you or moving away from you, the frequency would change. So we have the source moving towards it could be the source moving towards the observer or the source moving away from the observer. In this question, we have the source moving away from the observer. So we use this formula. Yes, we will use this formula. Let's just remember that the v in this formula will be the speed of sound, the speed the sound of itself is traveling. So we will have to find. We will know. I will give you the speed of sound, 343 meters per second. You use it back again here. This VO is the speed of the source, the initial speed of the source, and the VS is the speed of the source at the time they're asking us. And the time they're asking us is just before striking the ground. So we will use equations of motion to find VS first, and we will discover VS to be well, they didn't put a number in here, but they did a transposition. Oh, sorry. Right now, after we find VS, it's really simple. When you find VS here using the equation of motion, for if you drop if you just drop a rock down a well, right? You just drop the clock, and they gave us the height of the building or of the room. It's 50 meters from the ground, and you just have to find the velocity of this thing just before striking the ground, right? And when you find that VS, you put that value in here. We know the initial velocity of the clock was 0, and we know we put the speed of sound here and here. You substitute all those, and you're supposed to get 571 hertz. And that's it. If you understand those examples, please try to understand those examples. Alright, so I hope you guys will come to appreciate that whatever we focus on before the test will be almost exactly what would come in the test, right? So please, as early as possible, try to understand these examples we went through in this video. You will most likely see the video on Sunday or Monday. Don't wait until Thursday to panic. If Monday you don't understand something, panic on Monday and don't go home until you get it. Right? Remember that this is a very important course. You don't want to not pass the course and then have to wait until next year to redo the course to enter into UG, right? So yes, you don't understand something, please come fully prepared to work with your calculators, and let's fight this thing until we get it. We're winners, right? So all the best in working the examples. I'm gonna give you the PDFs to these I think you did in class also, right? So all the best, and let's hope for a better test next Friday, and a great final exam on the other Friday. All right, bye bye.